Okay, so welcome back. I hope everybody got a tea. We're still refining our logistics on the tea breaks, but that should improve. And it turns out because today we don't have a laboratory in the afternoon, then maybe it doesn't matter if we're 5 minutes late, so it should be okay. But now I'm going to give a talk, and I do a short self-introduction simply because there's nobody here to introduce me. And so you can see I was, past tense, I was professor at the Technische Universität in Germany. So I'm actually retired for several years. So, and I've been here on the Henry Ford chair. This is from mechanical engineering and was here all of November and now all of, February, March. And then maybe again in October this year or something. And so that's my background. So I'm actually Canadian. My English is actually native language. But I worked in Germany most of my life. Okay. So, and what I've prepared is a lecture, which I've never given before, by the way, on instabilities in interfacial phenomena. And this is, of course on measuring techniques. So you say, oh, why is he talking about instabilities? But I think at the end of the lecture, you'll realize why I'm doing that. But I have to also say the first part of the lecture is lots of really nice pictures and movies, and the last part of the lecture is a lot of equations. So, but I'm trying to put you in that it's not too difficult to understand. And I understand that some of you, if you're, let's say, from microbiology, you probably, these equations are a little bit too much. But that's okay. It's not so much the equations, it's the methodology that I want to convey in using these equations. And for the people, let's say, more in engineering, that I think it's important to be able to go back and understand the equations. Okay, anyways, that's my little introduction. And that's the content. So the introduction is generally about a little bit catching up with what Ashish has just told you. Why we want to look at that, and then 3 different instabilities I wanted to talk about. The Plateau-Rayleigh, the Kelvin-Helmholtz, and the Rayleigh-Taylor instability. And they're all rather important when we talk about capillarity and wettability. Okay, so this is my introduction, and it just simply says all of these pictures you can immediately understand, I think. You've all seen them in some form, one way or the other. And the question is, in all cases, those are instabilities. Those are bulk liquids that have started to deform, and they've deformed because something was unstable. So, and the question is, which instability? And we will talk in detail about 3, but there are more. Hydrodynamic instabilities. There are entire books about this, and I've put some literature also in the slides if you want to deepen your knowledge about the different instabilities and how to evaluate them. And these are now some further examples. This is a diesel injection spray, and that's a close-up of the first 3 millimeters. And over here, that's a flat fan spray nozzle that you'd use in agricultural spraying for crop spraying. And that, I don't know if anybody here owns a BMW 5 Series. But if you're lucky enough to own one, that's your windshield washer nozzle, and it's going back and forth and putting droplets on your windshield at 120 kilometers an hour or whatever. Okay, so these are the kind of, and you can see, you can see physically the instabilities there. Something's making this bulk liquid unstable and to break up, and that's what we want to talk about. So here I've put some additional instabilities, so I think this is supposed to work if I hold it long enough. So just a minute. Just a minute. I have to turn on I think it's the laser pointer, I'm not too sure. Let me just, there it is. So I'm going to talk about the Plateau-Rayleigh instability, the Kelvin-Helmholtz, and the Rayleigh-Taylor. But you can see there are other instabilities, the bending instability or the fingering instability. We're not going to talk about that. I'm trying to whet your appetite to, if it encounter these in the future, you can look and then, of course, in both of these cases, we have interface acceleration. In this case, we have acceleration parallel to one another, and here we have acceleration normal. But I will talk about those. Okay, so Some further examples of instabilities, and I guess everybody knows this is coming from the water faucet dripping and whatnot. Okay, basically instabilities occur only when there's some small disturbance to excite them. If there's no disturbance, they don't occur. Okay, so the aim of what we're talking about here is to say prediction of response of fluid systems to disturbances. Is it stable or is it unstable? So if you disturb something, will it go back to an equilibrium state, or will the disturbance grow infinitely and become unstable? And we do this in fluid mechanics all the time, and here we would say more hydrodynamics because it's the liquid, no? Okay, and then of course we say, well, if we want to somehow derive whether something's going to be stable or unstable, then what are the forces? Typically we're doing force balances or momentum balances, sometimes energy balances. And so in that case, what forces are working on us? We have viscous forces, and exactly what Ashish was talking about, surface tension forces. Now, sigma times L is a Newton. And well, I might just mention that in case you're getting confused. Some people use sigma for surface tension. I think he was using sigma n gamma. And if you're a physicist, you're probably using eta. Okay, but generally you know more or less what we're talking about. And then we have inertial forces, clearly, no? And so the other thing is we have to say, is something unstable in space or time? No, either could be. And then we have to say, what is the direction of acceleration involved? And this is, for instance, in that case, distinguishing between Kelvin, Helmholtz, and you'll see that. It's exactly the same derivation, but the same equation is for both, but depending on the direction of acceleration, we get one or the other. And then we have to consider, can we go with a linear analysis, so simplify the equations, throw away higher order terms, or do we have to consider nonlinear analysis? And here's an interesting, the linear analysis can predict this, but the linear analysis cannot predict this. Here you need the nonlinear analysis. We will not do the nonlinear analysis. That's not the point of this lecture. I could imagine giving you a lecture course all term long on instabilities. So, and I think Ashish mentioned his last lecture normally does in 5 different lecture periods. So we're just trying to introduce you a little bit to the subject with these lectures. Okay, this is a good example. This is an old experiment from my own laboratory, maybe 2001. And here we have a liquid sheet coming out of a nozzle. And in the one case, everything is laminar in the nozzle, and in the other case, everything is turbulent in the nozzle. And so you can see already the disturbance in the nozzle. That's the disturbance that excites the instability. And if you don't have a disturbance, then the instability doesn't grow. And here what happens is the disturbance comes actually already outside the nozzle, and then you can see waves that start to grow and become completely unstable. But if you have a disturbance very early, it goes immediately. So, and here this is from another PhD around 2005, a man from Bosch. So I did a lot of PhDs with Bosch, fuel injection. And so we made an injection nozzle with a rounded corner, so a very smooth, long nozzle. It remained laminar, and we made the same nozzle and put some obstacle in there so it would be quite turbulent, lots of disturbances. Now watch what happens outside the nozzle. You see, this one here doesn't atomize, only at very, very high Reynolds numbers, and this one here atomizes immediately. So I mean, if you were an engineer in internal combustion engines and you wanted good atomization for good mixture preparation in your combustion chamber, then you want a disturbance in your nozzle, and then it'll atomize immediately. No? Okay, but this is the idea behind the instability. You need a disturbance, and the stronger the disturbance, the faster the instability is going to grow. Same as laminar turbulent transition in fluid mechanics. And so this is actually, now the disturbance comes from aerodynamic disturbances outside the nozzle. We call that second wind-induced atomization. And this is prompt atomization. It just atomizes immediately. And this is the same thing. Here's a nice rounded nozzle. There's a nozzle with disturbance in the nozzle. You can see it's exactly the same conditions. Same fluid, same Reynolds number, everything is exactly the same. So you can see these disturbances. Now where they come from, we don't always know. It could be a little atmospheric disturbance or something. This is not going to concern us today. This is, but you have to have some disturbance. This is another example. Maybe you can read here. These are the Reynolds numbers changing. Now I've taken away disturbances. I've taken away the boundary layer in the nozzle. There's no boundary layer, and suddenly everything is stable. This one, I cannot explain that completely. So in the boundary layer, you're getting also disturbances. And if you take them away, then you have no, in this case, fragmentation of the sheet. Okay. So now comes the first slide with equations. But these are really important equations. I mean, this is real basic stuff you have to know. We call this the Taylor rim. So G.I. Taylor came about this very early, and 1959. And what I'm showing you here is basically everybody knows that if you had a liquid sheet, you get rims on the side. Or you see these rims everywhere. And the question is, where do these rims come from? And it's clear you can't have a sheet with a 90-degree edge. Yeah, because the curvature would be very, very small. The pressure would be infinite inside according to the Young-Laplace equation. So you can't have that. You have to have a rounded edge. And the question is it rounded like this, or does it bulge out? And clearly it bulges out. And now we do a force balance. We take now and say, okay, let's cut this thing right here and do a force balance. So you've got fluid. You've got a fluid from here going into the rim. So the rim is moving down the sheet. This is a liquid sheet now coming out of the, and what's holding it together? The surface tension here and the surface tension here. So we're going to put those. It's a force balance. So we're going to say now D is this. I've got my pointer on there. Sorry. So D is the diameter times B, now times rho, so that's m, times velocity squared. M velocity squared is our momentum, and that must be balanced by two sides times B times sigma. That's the force holding it together. And then you can see very clearly that the velocity of that rim eating up the sheet is this velocity. So I've used sigma here. No? So that's that we call normally the Taylor-Kulik velocity. So now I've just shown you here, I actually want to see that again myself because I have to explain something about it. Let's do it once again. Watch. See, there's the Taylor rim. There's the Taylor rim, and it'll eat up that sheet. And in fact, you'll even see fingers, and these droplets will eat up the fingers. And that's what I want to show in the next slide. That's what we just talked about. Now the Taylor rim. And if you had a finger with a drop sort of on the end, the same thing would happen. You get the same velocity. Okay, this is really important because this is one of the fragmentation measures and maybe you know this very experiment. You know the oscillating plates, and then you get beads on a string. Yeah, you get bead because you've got polymer. I don't know. It's non-Newtonian. You can try that at home if you want. Okay. Anyway, and the same thing's happening. You've got these things are eating up the fingers. Okay. So watch this one. Watch this one. This is corona detachment. It has nothing to do with COVID. Now, the Taylor rim eats up the sheet. So this was already 2017, so this has nothing to do with COVID. We were doing this corona detachment before. But now we're back to measuring techniques. Think about it. If we wanted to know the thickness of the film, when it just breaks, there, what's the thickness of the film? All we have to do is measure the velocity of the rim into the sheet, and we know the thickness. So in this case, we excited the rupture, the corona rupture, with a small needle. Here, the rim, the rim starts, here's the needle, the rim starts going like that. We track the rim velocity, and then we know the thickness here and here and here and here in time. So here's time, here's from here to here, and there in color is the thickness of the rim. So already we have a measuring technique. How do we get sheet thickness, or finger thickness, doesn't matter, by measuring tailor rim propagation. But of course you have to say, well, I'm measuring the tailor rim propagation normal to the rim. So it's a material velocity. So you have to, I mean, okay, there's some MATLAB programming here, obviously, some image processing you have to do. Okay, so that already tells us, we can use some of these principles in measuring techniques. So that was my introduction. And now we go to the Rayleigh, plateau Rayleigh instability, which is basically what we're seeing over here. And so this goes back to original work of both I think Ashish mentioned Rayleigh in his last talk briefly, Lord Rayleigh, and I've put a little bit of, so Plateau was not French, he was Belgium. he was not, okay, so you can read that, I don't have the time. So basically what we have is we have a liquid jet of some diameter, and this liquid jet has a small disturbance on it. Where that disturbance comes from, we're not going to talk about that now, but there's a small disturbance, so it's not exactly the same diameter. And then we ask the question, will it go back to be a straight cylinder, or will it get unstable and become drops? And obviously, under certain conditions, it becomes unstable. That's what we're looking at here. And the question is when. And so the assumptions we're going to make is that it's incompressible Newtonian fluid. It's an axisymmetric shape. Doesn't matter, even with the disturbance, it stays axisymmetric. It's no dynamic influence from the ambient air, so no aerodynamic effects. It could be in a vacuum exactly the same. And then we would say that there's some small deformation, disturbance, and the viscosity, I'm going to show you the derivation without viscosity, but Weber did it with viscosity, and I'll show you the result with viscosity also. And okay, and we know that surface energy is minimized. We've just learned that from Ashish, and gravity and viscous forces will, for the most part, will neglect. But I'm actually now showing you the end result. And then we're going to look a little bit at the derivation. The end result for the viscous case is that there's some wavelength which is most unstable. Different wavelengths have different growth rates, but the growth rate, the maximum growth rate, has this wavelength, and that means, so sometimes we say wave number or wavelength. No? It depends how you want to do it. And what turns out then is that the drop size, if you say, well, everything there turns into one drop, then how much liquid was there? Well, it's this wavelength times the diameter of the jet, times the area of pi d squared divided by 4 or something. And so that gives you the volume, so here's the volume from here to here, and that's the volume of the drop that comes out. And so you solve for d, and you can see now you can solve exactly how big is each drop given an initial diameter of the jet. So so you can see a small jet will make smaller droplets, a big jet, and that, how big that is, well, it depends on this K optimal, and that's we will learn how big that is now. And it's roughly with viscosity a little bit different, and this is expressed with the Ohnesorg number, which has viscosity in it. So these are from Weber, or from Günter Brenn, and Günter Brenn gave me this slide last week, so he helped me a little bit. Okay, so now I'm going to derive it, and this is useful to learn. and because this is the way all instabilities are derived. And what I've tried to do is shown here. You can imagine this surface in this copper color. This is a surface, and you can see there's a saddle point in there. It's like two mountains, and between is a saddle point. And we can see that there's a curvature. At this point, there are two curvatures. These are the main axes. There's a curvature in this direction, and there's a curvature in this direction. And so one is positive and one is negative. No? And so we know the Laplace equation, so Ashish just derived that a little bit in the last, and we have two curvatures. One is going to be negative, so it's going to be a negative sign here. And so let's take a look. R1 and R2, here we have an R1 and an R2, and the pressure between here and here, so outside and inside, this is sort of the contour of a liquid surface. The pressure inside will be sigma times that curvature effect. No? Okay, now we've got, so this is my liquid jet with a small disturbance. No? I mean, I've exaggerated the disturbance so everybody can see it well. And so let's go. If we wanted to know the pressure here, how would we find the pressure here? So we assume the pressure is everywhere the same across the jet. So we have a curvature here, this curvature, and we have this curvature. So we have to do 1 over the y, and we get the pressure here. So that, and this is the second curvature. And what happened if we wanted to know the pressure here? Well, I put it here, so I had some space. So here's also, we have a curvature there, and now we have a curvature here. And you can see this one will be one sign, this will be the same sign. This will be one sign, and this will be the negative. It's a negative pressure because it's convex, no? It's not concave. Both here are concave, so it's both same sign, no? Plus. Okay, so let's work that out. I mean, we know here the pressure is going to be larger than the pressure outside. It's like in the droplet. Both are convex. Droplet is convex. And so the pressure is higher here. So I've put pressure is higher here. And on this one, so on this, sorry, the pressure here, I should have put it over here. The pressure on this narrow part will also be larger than P0. And the question is, which one is bigger? And it's very clear. This one here, so these are very low radii, long radii, so that won't make too much difference. But this becomes, of course, much smaller than this one. So the pressure here is higher than the pressure here. So I've put P plus is higher than P minus. This 0 should be, no, I put it here. No, that's correct. Now that's correct. So that means the pressure here is higher than the pressure here, so the flow wants to go like that. And that increases the deformation. It's unstable. That's the instability. So I've called that a phenomenological explanation of instability. It's an intuitive explanation. It's not yet a mathematical explanation. But it's very clear. I mean, it's going to be unstable under these conditions. The question is, what are exactly the conditions under which that, this one pressure here will be larger than that pressure there. That's what we have to work out mathematically. So for all the biologists in the room now, you can go to sleep for 5 minutes while I do the derivation. You understand the physics, that's the important thing. If you understand the physics, then you always have some motivation to understand the mathematics after. But let's do the mathematics. And this is actually interesting because this is the way you approach all instabilities. You do a perturbation analysis. And this perturbation analysis is quite simple. You have some steady state and you have a perturbed state. And so you say, well, now I have a small perturbation. So R0 is now R0 plus some small amount, a small perturbation. And then the pressure in here will also be slightly different. We're going to leave the surface tension, and the rho is constant. That was incompressible surface tension. There's no reason that should change. And so we're going to say the new R, the disturbed R, I've called it R prime, will now be R0 plus a small disturbance, and now we have to say, okay, this disturbance can be in time and space. And so we just make it sinusoidal. So sine plus cosine, e to the minus something. And we're allowing time and space variations. Okay, so, and then we say, well, it's non-viscous, so we don't use the Navier-Stokes equations, we use the Euler equations. And then we said it's going to be a linear analysis, so we throw away all the higher order terms and we make them linearized. And we have two equations in R and Z. We don't bother with the circumferential direction because we said it's axisymmetric. Okay, so we don't need it. So we have two equations, and now you can see we're simplifying. So it's not too difficult. And so and then we have continuity equation in cylindrical. So whatever sort of, whatever goes from here to here, we have to account for that in continuity. And so now we continue and we say, okay, we have now velocities. Normally everything would be zero. But now we're going to say, well, each velocity changes slightly. We're going to have a small radial velocity where this disturbance is. We're going to have an axial velocity, and the pressure is going to change. And we're going to make them, we're going to hypothesize that they change the same way that R is changing, this disturbance, with some sinusoidal variation, cosine sine, in time and space. No? And so we can put all of that into our basic equations, and we can actually then, so I'm a little bit fast, but I think you'll follow everything on the slides if you sit at home and look. So you can reduce all of that into an equation and reduce P and Z into this form with the continuity equation. And then you get that R, so the radius as a function of so this is the new radius, is C I1, and I1 is a Bessel function of order 1. Okay, so these are, but we have a constant, and that constant is given by the boundary. It's like always, you need the boundary conditions to get the constants. So this is an infinite number of solutions, but the one we want, we define with our boundary conditions. Okay, and so we have two boundary conditions. The first is kinematic, and it just simply says the rate of change of the radius r prime must be equal to ur at r equal to r0. So if this is the liquid jet and it bulges out, the velocity at the edge has to be ur. So, and that's exactly r prime. So that's the kinematic, and you can reduce then and get a value then for C. And then the other is the Laplace pressure. That's the other boundary condition. So we know that if this bulges out, then we have this R, and we have this R, and so R1 is just simply R prime. That's this. That's the one R. So that's simple, R1. We get that immediately, and we can then do I think this is a Taylor series expansion, I think, if I see that you put that up there. So it's a Taylor series expansion, so you can get it in the form like that. And then the R2, this is a little more difficult. What is the curvature of this? Okay, I'm not going to derive that, but it's fairly simple, and if you haven't ever learned that, you should. It's quite simple, and it's just simply given with the second derivative of R prime in Z. And this is a very useful formula, by the way. You can look it up in a table. And that gives us the R2, and then you can put everything into the Laplace equation. We know P0 in the case of no perturbation. That's just simply, that's the Laplace equation for a cylinder. And so we can put it all in here and get P prime, and that's one equation we have for P prime. And the other equation came from before, and so I've actually taken the one from before and the one we just derived, and we can say, well, P prime has to be the same, and we can then equate the two, and if we do that, we get that equation, and that's what's called the dispersion relation. And the dispersion relation you always have in instability, and basically it tells you that if there is a positive real part, then the thing grows. And if there's not a positive real part, it damps out again. And because it's the I omega t, no? And if that's growing in time, then it blows up. And e to the minus I omega t. No? And so you can see for here the dispersion relation has a certain maximum at some wave number, and that's that lambda optimal we were looking for. That's the wave number that's going to dominate. And it turns out that it's 0.697 or something. And, okay, it's a little bit, I'm going a little bit fast, but that gives you then, omega is 2 pi f. And f is, of course, I think I do that here. Well, f is lambda times f is sorry, u time f lambda is the velocity. So you can go back and get the lambda. So it turns out that without viscosity, the drop diameter will be, oh, this is not correct. This should be the large, oh, that's correct. The drop diameter will be roughly 2 times the diameter of the liquid jet, roughly. Okay, and the one I gave before with the Ohnesorg number was with viscosity. That's a little bit more complicated to derive. So we can say size of drops formed by inviscid jet breakup is about twice the orifice diameter. So then this is the linear analysis, and so you can see if you had satellite droplets, you don't get this with the linear analysis. But okay, there's a lot of detail there, and I went rather quickly, but I think the idea is in all of these instability cases, you do a perturbation analysis by perturbing a little bit the basic governing equations, linearize them, and then go back and find this dispersion relation. Okay, and then I go now to the Kelvin-Helmholtz. And I think this picture already says a lot. That's the Kelvin-Helmholtz situation, and this is so Kelvin here, Lord Thomson, and Helmholtz, Hermann von Helmholtz, who did a lot of other things, by the way, especially an electrical engineer, and I'm sure you've heard of him. Okay, he was also, by the way, a philosopher. Okay, and so the Kelvin-Helmholtz instability produces this kind of wave motion when we have two fluids of different density, or two fluids with different velocity, in fact. And this instability is often you see in the atmosphere, but a lot of other places. And the onset is related to the shear forces driving vortical motion between these two fluids. And I have an example. This is an example we did a few weeks ago at IISc. And basically what we're doing is this droplet is experiencing shock wave that goes by it. So we produce a shock wave that goes by the drop, and watch it completely disintegrates. And now we're doing really close up the shock wave you can see coming by, and you can see the deformation of the droplet. Yeah? So you've got a very high velocity fluid here, a different velocity here, and also, by the way, different densities. I think it might be a water droplet, I'm not sure. I think one is a water droplet and one is a liquid metal at room temperature. And in both cases they look similar, and you can see the Kelvin-Helmholtz waves, and you can see their wavelength. So this is the instability which atomizes droplets in supersonic atomizers, which is how you, by the way, make metal powders for your laser bed fusion additive manufacturing. You have to make metal powders, and you do it with supersonic atomization. Okay, and that's what we're doing at IISc just now. And so this is another example, Kelvin-Helmholtz waves. I mean, it's artwork. And so maybe it's interesting to understand where they come from. And so we have now the situation being treated as inviscid irrotational flow. So we have one flow here, and an interface. And so it's a potential flow. We can put the potential well, we should have 1 and 2 here, phi 1 and 2. And if you go far away, of course, the potential is 0. And so in continuity, it's incompressible. So we have the continuity. Here we are, just a minute. Take some time here, the continuity. And so again, on the interface, we have a kinematic situation. We have to say, okay, on the interface, the interface is going up and down, let's say, with a small amount epsilon h. So this is similar to the last time we had. We're perturbing this interface a little bit by epsilon times the some h, and so we get a small perturbation, and then we say, okay, kinematically that small perturbation, the material change of that small perturbation, we can then express in terms of our potential, and then we can, if we neglect the higher order terms, we get the potential for both phi1 and for phi2. Okay, and again, this is probably too fast, but it gives you the idea of how we go about that. And then we say the continue across the interface, so there's no strong curvature to start. And again, across the interface, the pressure has to be the same. And so this is just Bernoulli equation. I think maybe some of you already recognize that with the potential. The Bernoulli equation, we have to equate the two above and below because there's no jump until we start getting curvature. And then we basically say, okay, like we did in the last case, now we have to postulate how are things going to change. And last time we postulated changes of R and pressure and what did we, UR, U, Z, and pressure, I think we postulated being changing in time and space. And here we're postulating changes of the interface height and changes of the two potentials in space and time. Yeah? And S is then omega, so to say, I omega. And I think I said that, yeah. S is I omega, no? So it's omega t, no? With cos and sine. And so again, these things will grow if k is larger than 0. Yeah? Because then we'll have I positive, and that will grow in space. And or if this is a real part larger than 0. And then the interface is unstable. So, and again, now comes lots of equations, but I think you'll be able to follow them all at home, you know, when you look at slides, or if you have to come back to this. And we have some boundary conditions, and again, we get a quadratic equation and a dispersion relation. And I've put it in a final form here. S, so I omega S 2 pi f, now this is now S 2 pi f is equal to that. And we said that's imaginary, that's real, and if it has a positive real part, the thing grows. That's all we have to know. That's the dispersion relation. You can plot that and see where at what k it grows the maximum. And we can already see, though, that the condition for that to grow is this. You can do some multiplication there. That's the condition. In fact, you can even take out the k and solve for k. K must be larger than, put all of that on the other side, and k must be large, and then the thing is unstable. So for certain wavelengths, k is 2 pi divided by lambda, no? For certain wavelengths, the thing's going to be unstable given a velocity difference and a density difference. That's what we wanted to find out. So I think everybody, some are nodding. It's clear I skipped a few steps in the last slides, but that's what we want. And so we can say if U1 is not equal to U2, then this is always positive, or because it's squared. So this is always positive. So you can always make that bigger than that if k is large enough. Because here's you've got k squared, and there's you've got k. Or you can divide it out, it doesn't matter. So as long as you've got a difference in velocity, there'll always be a wave number that's unstable. And it'll become unstable. No? So, and that's what you see also in the atmosphere. It just might be for, k has to be big, that means the wavelength has to be small, no? 2 pi divided by lambda. So for short wavelengths, it's always going to be unstable. Okay, and of course, now back to measuring techniques. The interesting thing is now, of course, to measure the wavelength and to see if it agrees with the dispersion relation, and then you know if you have Kelvin-Helmholtz. And I did that yesterday with Ahmed Said in the group of Mahesh. He was doing crowds. So you have a lot of people trying to get into the building and come out of the building, and then you have a shear layer, and then he's seeing rolls up, and we're measuring the wavelength, so simulations, and seeing are those Kelvin-Helmholtz. So do people moving in and out of the building behave like a continuum? Continuum mechanics. That's actually an interesting idea. Okay, so, and now if we had a stationary body of water, so you've got a lake, the swimming pool, out here at IIT Madras, and there's a wind, do you get waves? Huh? So U2 is equal to 0. There's nothing moving in the swimming pool. Rho 2 is much larger than rho 1, air, water compared to air. And then you can go back to the S equation. Well, I won't do it. I think it's clear. Sorry. Now I've got myself all mixed up here. Okay, and you can see that this is the dispersion. Now it becomes the instability condition. So let's do let's say we had 10 meters per second. Then we put the 10 meters a second, and we know rho 2 and rho 1 and g. And we can go and we say, well, that means sort of a wavelength of about 80 centimeters. So if you're standing beside the swimming pool early morning and the wind is 10 meters a second, you should see waves of about 80 centimeters wavelength. That's the... Okay, and then if U1 and U2 are equal to 0, but you have a density difference, is it unstable? So nothing moving. Okay, well, you can go back to the S equation, and so S was I omega, no? And we get this this relation, and then you can see, well, we can see now the phase velocity. So I've tried to put here what we call the phase velocity is F times lambda. How fast does the wave go by us? How often? And that gives you meters per second, which is just F is 2 pi, omega is 2 pi F, and lambda is 2 pi divided by K, so you get this. And we know omega is, S is I omega, so we had the S equation. So we can take the S equation divided by K, and we get this. And then we can end up, we define that as, the square root of that as the Atwood number, and we get this rather simple equation. Okay, so that also is unstable for certain conditions, and that's what we see also in here. So, and then we have the case of a simple vortex sheet where the rhos are the same. That would be, let's say, in the atmosphere, and then we also can get the convective velocity, and it turns out to be basically it's the average velocity. So U1 plus U2 divided by 2. So it's half the it's the average velocity. Yeah. Okay, so this gives you actually some consequences of the Kelvin-Hall, and we measure that, of course, the wavelength. And then I just add, now it's about time to stop, but I add simply the following, is that if we had viscosity, then you can do the same. It's more complicated, and the only thing that changes, that's exactly the same S equation from before. The only thing that changes is you get that. And now take a look. Now, to get that side, remember we had to get that had to be positive, real. That's the real part. Here's the imaginary. That's the real part. It has to be positive. And so we can say, I've just repeated that equation here, the cubic term will dominate the large wave numbers. Yeah? So surface, basically the kappa is like a K. We can say it's like a K. So the surface tension strongly resists high curvature. So it damps it out. No? The surface tension tries to damp out curvature, so the linear gravitational term will be largest when kappa is small, so that long wavelengths will be unstable if we have this case. So basically, the most unstable case we've done, I've simplified it now. I just simply bring an example that's here, and so here's the example. Driving waves on a lake, this is now with the viscosity, here's the surface tension, would be 6.6 meters a second. That's the necessary speed to get the waves on the lake. And that's critical wind speed, you have 1.7 centimeters wavelength. Okay, so this explains a lot of things you see around you in the world. Clearly the mathematics takes more time to present. But the methodology is, that's what I'm trying to get to. Make a perturbation, go through all the math, and then you get this dispersion relation. And now, this is only 2 slides, because it's exactly the same as the Kelvin-Helmholtz. So again, well, the Rayleigh-Taylor, and this is what we expect. You have a heavy fluid here, and a lighter fluid here, and the heavy fluid goes into the light, and it's unstable. So if you have a leak in the washroom upstairs, and there's some water on the top, on the ceiling, it falls down. But if you have a puddle of water here, it doesn't fall up. That's the Rayleigh-Taylor instability. So if there's a small perturbation, it comes down into the lighter fluid. Here, if there's a small perturbation, a small wave, it doesn't come up any further. And that's exactly the same dispersion relation as we just made for the Kelvin-Helmholtz. In fact, we have exactly the same situation here. Watch. That takes a minute. Yeah. So this is exactly the same condition we had in the last slide, but now rho 2 is larger than rho 1. Sorry, the other way around. I had rho 1 on top, didn't I? Rho 1 is larger than rho 2. Yeah? So you have the heavy fluid on top of that. And so we have basically what we have is we have a heavy fluid up here and a light fluid here. So gravity is in this direction. So acceleration is in this direction. So we have an instability. And this is the Rayleigh-Taylor instability. However, in fact, even if you have an acceleration not due to gravity but due to something else, so if you have a heavy fluid here and for some reason it's accelerating against a light fluid, for instance it's rotating, so you have a centrifugal force, then it will break through the heavy fluid into the light fluid, exactly the same. And so you can get all kinds of even fingering if you have a droplet spreading out into air. So it impacts some and starts to spread out. You have a heavy fluid accelerating into a lighter fluid, Rayleigh-Taylor instability. And you get like fingering. And so, in fact, you can explain it slightly different, clinic torque, but it's exactly the same equation. And that's what I tried to show here, that this will always be, I mean, this is larger than that, so this is always small, so this is always larger than that. And that's the problem. It's just unstable when you have stratified in-density, stratified situation. So that's actually all I wanted to tell you about. That's the original work from Rayleigh, and some of the best work is from Chandrasekhar. His book on hydrodynamic and hydrodynamic stability. Almost everything comes from Chandrasekhar. All the subsequent pieces on these things. So I realize a lot of equation, I warned you. But what I'm trying to do is interest you for this type of thing. And you can see for the measurement techniques, this is really absolutely essential that we understand what we want to measure. And one of the things we have to now measure are things like wavelengths, which we do with image processing. That comes partly today and partly tomorrow. Okay, I think I'm already over time. So I stopped there, and I'm doing my self-moderation. So now is the time for questions, and then I think there's supposed to be again something outside, maybe more punctual than the last time. So thanks a lot for the attention, and we move to the questions then.
So if you impose any boundary condition, then how the dispersion will be? So here there is no boundary condition, we are not putting to the flow.
No. Here we have still the boundary condition. We have the kinematic boundary condition, and we have the Laplace boundary. Both we still have in developing that equation, that dispersion relation for the Kelvin-Helmholtz, and that's also valid for the Rayleigh-Taylor. Those were the two kinematic conditions one kinematic and one Laplace. Those were the boundary conditions.
So for example, if we increase the chamber pressure where the dispersion is happening, so in that case the boundary...
The P0 you mean?
Yeah.
So, or maybe I didn't understand.
Yeah, PA external, yes.
Yeah, okay, I mean, that's, you could call that boundary condition, but okay, if you go back to the Laplace equation, the Laplace-Young equation, it's a delta P. So if you change, let's say, one of the domains in pressure, all we're saying with the Young-Laplace equation that if you go across a curved interface, the pressure changes. The absolute pressure doesn't play a role. Or, I don't know if I understood the question.
Yes.
And by the way, in the Navier-Stokes equations, the pressure never enters. It's always pressure gradient. And the absolute pressure only plays a role insofar that the pressure can naturally influence the material properties like viscosity or even surface tension. Think about it, if you increase pressure, so you have, let's say, water in some atmosphere, and you increase pressure and pressure and pressure and get up to the critical pressure or temperature, critical thermodynamic critical point, then basically you can't distinguish between a liquid and a gas. So the surface tension would have to go to zero. And it basically does, but then it becomes a little more complicated. Then it's like a layer, a surface layer, a finite layer.
Thank you. And then for the non-viscous fluid, you mentioned it's a 2 times of diameter, the optimal diameter. For viscous fluid, how the diameter is?
Yeah. So I hope that I understand the one you're talking about. If we go to this, I think was this one you were talking about? Yeah. This was for viscous, and this was for non-viscous. And so the diameter of the drop is equal to that. But if we take a slightly different derivation to get the other K optimal with viscosity, then the drop diameter is equal to diameter times that. And that has the viscosity in it, so it changes. Yeah, and this was done by Weber, and Bren has derived that very nicely. I didn't do it; it's more complicated. It takes longer, but this changes viscous fluid. Yeah.
Professor, in slide number 30, you have shown an interesting phenomenon in which shock wave is interacting with a droplet.
Slide 20?
30.
30.
Yeah.
Sorry.
The experiment which you did at ISC. Yeah. So I'm just curious, like, what is the die of that chamber and die of droplet which you was analyzing?
The diameter of the droplet.
Yeah, and like I'm thinking that whether the shock wave was entirely encapsulating the shock wave, that droplet, or like some part of the droplet was only interacting with the shock wave.
Yeah. This will. You'll hear a little bit about that in the next lecture. So what we do is actually we do it differently now. We've turned that thing sideways and we hold the droplet in an acoustic levitator. So we levitate the droplet and a shock wave comes by. But the problem is a really important problem. So we want to see different things. We want to see the entire atomization of the droplet, and then we need a big field of view. But then we don't see this detail. And so what we've done is we've done several different experiments. We've done experiments with large field of view. And this experiment, that droplet, I think, is about 2 millimeters, 2 mm in diameter. I'm not exactly sure, but it's published, so I can look. And then what we did is we took what we call a long-distance microscope. And then we zeroed in our field of view very small. And we managed to capture these very first few microseconds. That's how we did it. And the illumination is also, I think we used a Cavilux laser or something, I don't know. So it's, well, you'll hear about that in the next lecture about the long-distance microscope. Yeah. It's difficult.
One more question, Professor. What is the significance of that imaginary part which we are getting in the solution? Like, is having no significance, or like we can exploit in some way?
No, normally we don't even bother about it too much. Yeah. It's for the stability analysis. Yeah.
And one last question, like in inkjet printing, so there are cases when satellite droplet formation occurs, and I think that we tend to develop some technology in which there is a minimization of that satellite droplet formation.
Yeah.
So, is there a technique?
Thank you so much for that question. I think I understand the question already. Right? So, or continue, sorry?
No, is there any technique to minimize the instability which we are getting in that case?
So this is probably, I should have put a few slides about this. But basically, in inkjet printing, what you do, you have a little hole, the ink goes through the hole, and then you want droplets 2 times the size of the hole. So roughly 1.89 or whatever. And how do you do that? Well, you know it's unstable to a certain wavelength, and I showed the dispersion relation, and we know the wavelength where it's most unstable. So we vibrate the hole at exactly that frequency, and then we get exactly that wavelength, and that's what we call a monodispersed droplet generator. And that was done by Berglund Liu back in 60s, or I don't know. And that's that you can buy these things, and there's a monodispersed. And the inkjet printer is very similar. You have to have some disturbance, and instead of vibrating the hole, because typically these inkjet printer heads, they'll have 300 or 400 holes in them, and instead of vibrating the whole thing, what you do is you have a piezoelectric transducer on the volume above, and you vibrate the pressure. You excite, you make a pressure oscillation, and that's the disturbance. So now we are talking about how do you make the disturbance. That's the disturbance, and that's how the inkjet printer basically works. And I think, and what you're now saying is, are you sure it's stable? Or do you get satellite droplets? Because satellite droplets, as soon as you get the hole clogging or any dirt or anything, then you get satellite droplets, which will destroy your printing. I mean, it just messes up the printing. And so, I mean, this is really a problem. Of course, one thing is you have to make sure that the liquid is very clean so that there's no clogging in the hole. The other thing is also by the way these holes, the way they're manufactured is very important. They do get sort of a rounding at the beginning. And otherwise, you have to keep your frequencies very monotonic or monotone. Not monotonic, monotone. So that it's... And then... the rest is probably top secret, and I probably won't know. But I think a lot has to do with the properties of the liquid and the recipes used, and some of them are not completely Newtonian. And to be honest, these are probably completely trade secrets. But they have an effect.
One question regarding that ultrasonic atomizer you were saying,
Yeah.
droplet generator. So you are giving a equation, diameter is equal to 2 times the hole size. But I have seen in literature, and we have also one droplet generator. We are having a similar droplet size similar to the hole. Whatever we are having like if we are having 0.2 mm diameter, the diameter, the drop size we are getting is also similar to that. But you are giving it twice the diameter of the hole size.
But this dispersion relation, you saw that it sort of goes up and down, and you can excite at other wavelengths, and you can make it work at other wavelengths. But generally we try, especially for you try and do it at the most favorable wavelength. But you can get other drop sizes, sure. And normally, this is what we find is, so what we do is when we're using the drop generators, then we always have a backlighting camera on it, so we can also see how regular everything is, because it's a drop chain that comes out. And then we can change the frequency of the disturbance, and we can see, they're changing a little bit, and of course the distance between, and how many, the frequency. And then we can see, it's stable between here and here, and if we go too high or too low, then it becomes unstable. So there's a range in which it will still work. So, I mean, if you increase the frequency of your disturbance, then of course you get a shorter wavelength and smaller drops. And if you decrease the frequency, you get bigger drops, but you can't go all the way you can't go to infinity in both directions. It just doesn't work. Then it's no longer unstable. Yeah, but and you have to monitor it. You can't trust that it's working because you don't know. It might be clogged, it might be dirty, and you never know. You always have to watch on these things, and that's the problem with the inkjet, is they're always watching, in some way monitoring, and that's why they have so many holes in these things, because they have a high degree of redundancy. And then what happens is the software, it's an entire industry, the software to monitor the product as it's going and turn on and off different holes. They already, these are no longer working, and these are no longer, we have to use other ones. And sometimes there's not enough to make it, and then they combine different holes to make a workaround. And this is an entire software industry to control these print heads. and these printheads have to be changed regularly. Turns out I was in the same hostel as a Swiss guy who made a company out of this, and he has now 350 people working for him, just doing software for printheads. A Swiss fella, and he's very rich, by the way, also, which you have to be to live in Switzerland, okay?
In the slide 41, you talk about the dispersion relation including surface tension.
Yeah, that's that last term, no?
Yeah, their kappa is the same order of this K, or they might be different.
Yeah.
I have seen that in place of kappa, I have seen wave number.
Yeah, okay. I skipped over that, but I can describe it very simply. If we now add the situation of surface tension, then we have to remember there were always two curvatures to get the pressure difference. Then we must go to 3 dimensions. You see, before I was working axisymmetric, only 2 dimensions, Z and R. I didn't worry about this dimension. But if we add surface tension, I need the 3rd dimension. So instead of the curvature just in one direction, we need the additional direction, and so we have to now put also in the Z direction, we also have to put a term. And now kappa is capturing what we had before in the Z, in the X and the T, and now we also have the L squared. So kappa is like K, but it adds the 3rd dimension. And so now we have kappa instead of K here. And basically what we can say is that here we have, I think, to be quite honest, yeah, this is okay. This is okay. It's all in here. But basically, I think when I went to use that, here I've added it, and here I've said if it's small, and then at one point I think I put for the most unstable case, L is equal to 0, and then we can go back using kappa.
So that comes from square theorem.
That's the Square's theorem for 3-dimensional instability, yeah. And I didn't. I think I just mentioned that it's Square's theorem. So that would be sort of in the advanced course. I don't know. Yeah, it adds the 3rd dimension. But you understand, you need the 3rd dimension for the Laplacian equation.